Tonight's speaker is Rick Boozer. Rick has been here before. The last time he was here about just over a year ago, I think maybe a year and a half ago. Rick's from Greer, South Carolina. Rick is he has a master's in astronomy, and he's a speaker and author. He also teaches astronomy at Spartanburg Community College. And he's also an author. He has a book called The Plundering of NASA, an expose. It's how to get America really back on track to get our manned space program back going to be the leader like we used to be. Okay, so after that, Rick, I'd like you to come up and everybody introduce welcome.
Well, it's so nice to be back. Julie and I always feel so welcome here. We enjoy our times that we come up here and I do these presentations. Anyway, can everybody hear me first of all? Really, whether I had this microphone on or not, you could probably hear me all the way to the back of the room. I get complaints when I'm teaching my classes from people down the hall hearing my lecture. I have to close the door. I'm just a loud speaker. Anyway, Galileo has always been a kind of a hero of mine ever since I was a kid. And Julie and I, for our 30th anniversary, we went to Italy. We went to Venice, Florence, which was Galileo's hometown, and Rome. And of course, we couldn't visit Florence without me going to the museum named after the great man. And that's what this presentation is about. The whole museum is centered around the Medici collection of scientific instruments. How many of you know who the Medicis were? Well, quite a few of you know your history then. They were the most powerful, influential family in Europe, really, during the medieval times and the Renaissance. They were the bankers not only to, did this just, yes, still going. Not only to the merchants and so on, but actually whole entire countries, kings and queens of Europe. And so it was no accident that Florence was the birthplace of the Renaissance, because they were the richest place in all of Europe. And it was considered the in thing to be building up civilizations to reach the heights that they considered a civilization was before the Dark Ages. And so the Medicis financed all these great artists like Michelangelo and Botticelli and Leonardo. And they also considered themselves aficionados of the sciences. So they would also be patrons of such people as Galileo and Torricelli, the guy who invented the barometer. So there's no surprise that Florence was the city that brought essentially Europe out of the Dark Ages and started the Renaissance, because they had the Medicis and the other powerful families in that city had all this money, and they wanted to show how refined they were, and so on. All right. So, anyway, so the Medici collection contains instruments that go back well over 1,000 years. Of course, like I said, this is our 30th anniversary. We started out in Venice, so of course we had the obligatory story gondola ride. So I just thought I'd show that, kick that in there.
But you look happy.
Yeah, we were.
They sit together.
Yeah. We play nice. We play nice together. Oh, wait, thank you. All right, now I think we got it okay here. So anyway, we went to the Museo Galileo in downtown Florence, and it contains the Medici collection of scientific instruments. This is the converted 16th century palace that we stayed in, converted to a hotel while we were there. And even it was like walking through a museum. You see the statues and everything through there. Now, before we get into talking about Galileo, I'm going to talk about somebody. Everybody knows that Galileo caught hell from the Inquisition. But there was a guy a couple of decades before him that caught even worse hell. A guy by the name of Giordano Bruno. And he got in trouble with the Catholic Church. Some of it was on theological grounds, but some of it was, just like Galileo, for saying the earth is not the center of the universe. And he even went farther than Copernicus. Copernicus said, no, the earth is not the center of the universe. The sun is the center of the universe, and everything goes around the sun. Giordano Bruno said that, no, Copernicus, you don't quite have it right. Yes, all the planets go around the sun, but the sun is, all those stars we see in the sky, those are suns. And they probably have planets going around them. And not only that, since those are other suns and they have planets going around them, there's probably Earth-like planets there with intelligent beings on them. And he got barbecued for that. At that very place, with a beautiful sounding name, translated from Italian, that means field of flowers. This Campo de Fiori, and this statue at Campo de Fiori marks the spot where he was burned at the stake. And later on in the 1800s, he was celebrated as an advanced thinker and scientific mind. And so in the late 1800s, this statue to him was built in Rome at Campo di Fiore, where he was burned at the stake. So, we'll talk about why Galileo didn't meet the same fate in just a little bit. Now here's the outside of the Museo Galileo, which is old in and of its own right. This bottom part here, this used to be up to this level here was a building. It was built in the year 1060. That's how old that is. This other part was built in the 1500s. So the building itself is quite an antiquity. Now, as I told you, the star of the museum, there's much more to the museum than this, as if this isn't enough, the Medici collection, which, as I told you, the stuff in the Medici collection goes back 1,000 years. If you look at this astrolabe right here, just used to measure the elevations of stars and so on, this was owned by an Arab philosopher sometime in the 900s AD, the 10th century. This celestial globe was owned by the prominent philosopher, scientist, mathematician, Arab philosopher, scientist, mathematician Ibrahim ibn Sa'id. This dates from 1060. Celestial globe, you can't really see the stars and constellations on it there, but it goes back that far. If you look at this, this is one of the stars of the museum, Antonio Santucci's armillary sphere. And this armillary sphere is a representation of the Ptolemaic view of the universe, where it was thought the stars and the planets and the sun all rotated around the earth. And of course that was overturned by Copernicus and Kepler and Galileo and all those guys. But the thing about it was, there was a guy called Aristarchus around 2500 BC who figured that the sun was the center of the universe and the planets all went around the sun, and the stars were so far away that you couldn't see them move. But how many of you know the principle of parallax? Okay? But what that says is, if something is relatively close to you, and you can check this out with your eye, if something is relatively close to you, you put one hand over your eye, that eye sees it in one direction, you put one hand over the other eye, that shift in position, that's parallax. So the closer something is to you, the more you'll see that shift in position. Well, they said if the Earth orbits the sun, it's going to have a very wide orbit. So, it takes the Earth 1 year to go around the sun, right? So, to go from one end of its orbit to the other is going to be 6 months. If you look at the same star at one side of the orbit and you wait 6 months, if the star, you should see a parallax if it's relatively close, right? And back then, and they still thought it up until Copernicus, hey, that makes no sense. Your idea that all the planets go around the sun and the stars are that far, the stars are out beyond, not going around the sun. We should be seeing a parallax 6 months later. The reason why we don't see a parallax is because they're so blooming far away, we don't have anything accurate enough to measure. They said that's absurd. Nothing could be that far away. And so, of course, now we know they are that far away, and it was not until the 1800s that we had instruments accurate enough to measure parallax even to the closest stars. So that's the reason why the Ptolemaic view of the universe held for so long. But anyway, so this is an armillary sphere made in the mid-1500s before the Ptolemaic system was toppled, showing, the way things orbit around the Earth. And the thing about it was, in order to make this thing accurate enough to predict the positions of the planets, they had to you not only had the planets following circles in the sky, but in order to be able to predict the positions, they had to put little subcircles to make things come out right, to get accurate predictions, because they weren't really going around the Earth. If they had an accurate model, they wouldn't have to add all this extra fancy circles within circles and everything like they had to do with this. So the sun-centered universe simplified things greatly, or sun-centered solar system. Really. Now, here, these date from the mid-1500s. These polyhedral dials, they were perpetual calendars. This 12-sided shape here You could use it to find the day of the week of any date of any year, going backward or forward into the future. So it's a perpetual calendar. All of these are different designs of perpetual calendars. Here is an astronomical clock dating, let's see what the date of that is. To the late 1500s. It could not only tell you the time, but predict the phases of the moon and so on. Very ornate, artistic work. Beautiful instruments. So this shows you some of the things, and you wouldn't believe thousands upon thousands of instruments, some of the things from before Galileo's time up until around Galileo's time. Then after that, just after Galileo's time, you see these early telescopes dating from the 1650s on up through the 1700s. Refractors in this case. How many of you know what a refractor is? Refractor telescope. Most of you should. Refractor telescope is the most basic kind of telescope. It uses a big lens to gather the light. A reflector telescope uses a big mirror, which most telescopes today, most modern telescopes, are reflectors. But early telescopes, and still, it depends on what you want to use it for. Some of your really good modern telescopes are refractors. Refractors back then were pretty crummy. But if you buy an expensive refractor today, Galileo would kill for it. Because it's just that far beyond. A mechanical calculator. It's used like to predict the trajectory of cannonballs by a military man or whatever. Here is a surveyor's theodolite, a little telescope. By the way, this right here, that dates to, let's see, that dates to the 1600s. This as well. This manual here is written in Italian, though. The manual that goes with this theodolite. Here's early guns, or as they called them back then, blunderbusses. From the 1500s on through the 1600s. Here's a static electricity generator, very similar to the one old Ben Franklin had. He had made to generate static electricity for his experiments. This dates from around his time. Here are some 19th century Gregorian reflectors. How many of you know the difference between a Gregorian reflector and a Cassegrainian reflector? A couple of you do. The difference is, those of you who are familiar with reflectors, in the case of first of all, you've got your Newtonian reflector, which has a concave mirror. It's invented by Isaac Newton. Got a concave mirror. The light comes back and hits that concave mirror, gets reflected off of another smaller mirror at a 45-degree angle and sent out the side of the tube where the eyepiece is. That was the very first reflector telescope that was invented by Isaac Newton. The Cassegrainian reflectors, some of you may be familiar with those. I have one. And there's also what is called the Schmidt Cassegrainians and so on. But a Cassegrainian reflector, again, all of these have a concave mirror as their objective, the main mirror that collects the light from the object. But a Cassegrainian reflector has a convex mirror that reflects light back in the direction toward the big mirror, but there's a hole in the big mirror where the light goes through back to the eyepiece to focus to see the image. The difference between a Cassegrainian reflector And a Gregorian reflector is, instead of the secondary being convex, it is concave. So that's the main difference. And by the way, if we have the time, I shouldn't have done that. If we have the time, remind me at the end of the lecture, and I'll tell you how a stupid mistake on Isaac Newton's part led him to invent the reflector telescope. Now, remember what I told you, the Medicis were the most powerful family really in Europe, and the richest. And this is the guy that's probably responsible for Galileo not being barbecued like Bruno was. He was a cardinal, very high-ranking cardinal, and a member of the Medici family, a great admirer of Galileo's work. His brother and his father were patrons of Galileo. They financed Galileo, and this guy kept him out of the fire. Cardinal Leopoldo de Medici, supporter and defender of Galileo, as I said, son of Cosimo II. And after Cosimo died, his brother became the head Medici. And also, Cosimo started being Galileo's patron, and Fernando II was his last patron. Closely followed Evangelista Torricelli. He was the guy who invented the barometer. And the unit used to measure barometric pressure, the torr, T-O-R-R, is named after him. Now, this was so cool when I got there. The great book of Galileo, the Sidereus Nuncius, where he announced all his great discoveries, where he, that the moon is not a perfect orb. Oh man, it's got craters on it. The powers that be didn't like that. No. God made all the celestial orbs perfect. There are no imperfections. The phases of Venus, and so on. All this, he wrote in a book and had it printed, but this is Galileo's own copy of the Sidereus Nuncius, which in English means the starry messenger. And this right here, there I was standing right in front of it, looking at it, it's Galileo's own handwriting, his annotations in his own copy of the book. Now, so by observing, Galileo showed, by observing the phases of Venus, watching Venus go through phases like the moon, he was able to show that Venus orbits around the sun, not the earth. They didn't like that worth of hanging. And by inference, all the other planets went around the sun. And when he turned his telescope on Jupiter and saw that Jupiter had some big moons going around it, he said, well, this is just like the solar system. You got the sun and the planets. Well, this is just a small model that shows you that, this kind of thing happens. You've got Jupiter here in place of the sun, and you've got these big moons going around it. And when Galileo was kind, if you don't mind, pardon my French, but Galileo was kind of an ass-kisser. Let's face it, the Medicis, his living depended on it. So he tried his best to, in this book, The Starry Messenger, he called the moons of Jupiter the Medici stars, and tried his best to get them be formally recognized as that. But what do we call them today, folks? The Galilean moons, or the Galilean satellites. They're named after him. So anyway, if you've ever seen any of the stuff any of the letters and everything that Galileo wrote to Cosimo or Ferdinand, it was, oh God, it's just about making you gag. You'd see it's kissing up so bad. But the language of these. But anyway, now what was even after he saw all this, he still disputed Kepler's claim that the orbits of the planets were ellipses. He said, no. I mean, he was using the same kind of faulty logic as the people that were blaming him. He said, the circle is a perfect shape. The planets should orbit in circles. And he just refused to believe that the planets didn't orbit in perfect circles. But the only way you could make the calculations come out right without a whole bunch of extra rigmarole was if they were elliptical. And Kepler proved mathematically that the shapes of the planets' orbits were elliptical. And he did that by using the data of a Danish guy by the name of Tycho Brahe, who was his teacher. Tycho Brahe was the first person to make instrumentation accurate enough, even before the telescope, right before the telescope, accurate enough to accurately measure the positions of the planets. But Tycho refused to believe Copernicus. And by the way, the only reason why Copernicus didn't get fried for saying what he did? He actually wrote up his theory 40 or 50 years before he died. But he waited until he was on his deathbed. And he, just right before he died, he said, okay, go ahead and publish it. So after I'm dead, I don't care. They can't touch me. So that's what he did. But Tycho didn't believe that. He said again, he used the parallax argument that the stars couldn't possibly be so far away that he couldn't measure the parallax. Well, his instruments were good for the day. He could do very accurate measurements of the planets. But like I said, the instrumentation that could actually measure the very small parallaxes of even the nearest stars didn't come along until the late 1800s. But his student, Kepler, took his data after Tycho died and figured out the actual shapes of the orbits of the planets. And found out they were elliptical, and came up with his 3 famous laws of planetary motion, which have been still used to this day, and which Newton later improved upon. Is there anything I forgot to mention? Yeah, that though Galileo, why he couldn't accept, he went against every other precept. Why couldn't he accept the ellipse? Well, it's kind of like Einstein when quantum theory came along. Relativity has been proven pretty well, and it's pretty darn accurate. But so has quantum theory, and it's even been proven pretty well then. But Einstein didn't like the fact that quantum theory says there are things that just happen due to chance. And to which he said, God does not play dice with the universe. And then Niels Bohr, the guy who figured out the structure of the hydrogen atom, says, quit telling God what to do. And so I guess that was just the same thing with Galileo. He just didn't want to believe it. And now we know, I mean, even all these years later, trial, quantum is held up just as well as Einstein's relativity has. Now, this was another exciting thing I saw there. These are two of Galileo's. This is the second telescope he ever made, and this is the third. This was made in 1609. This was made in early 1610. This is the objective, the main lens from the very first telescope he made. It's cracked. And they made this beautiful ornate gold thing to put the objective of his very first telescope in. Now Galileo did not invent the telescope. That was invented by a Dutchman by the name of Hans Lippershey. And the legend goes that really he didn't truly invent it, that it was his children, his son and his daughter. His son and his daughter supposedly, and I remember reading about this when I was a kid, he was trying to work, he was a lens maker, he was a spectacle maker. And his kids were kind of bothering him, and he says, here's a couple of lenses, go out and play with them. And one of them was a convex lens, and one of them was a concave lens, and according to the apocryphal story, whether or not this is true or not, one of the kids held the big lens in the front and the little lens in the back and looked at the church steeple far off and said, wow, this is coming in closer. And they go running home, the kids go running home and they show their father. And he just couldn't believe it. And so, well, the next logical step was for him to take those lenses and mount them in a tube. So that, anyway, is the legend. But it was Hans Lippershey who invented the telescope, a Dutch spectacle maker. So this is the objective from the very first telescope in this nice ornate mount. This is the second, this is the third. This is a replica of the parts of Galileo's telescope and replica of the tools he used. The tubes of his telescopes were paper mache. And so to make a tube, he would take one of these wooden dowels, wrap paper around it, lacquer it, let it harden, wrap another layer of paper around it, lacquer it, let it harden, and you have a pretty rigid tube once you're done. The focusing tubes were made the same way. He had dowel tools for wrapping paper and creating paper mache for those. So that shows you how he went about making a telescope. Like I said, paper mache parts.
And physically, how long is that? 3 feet or so?
Yeah, something like that. 3, 4. Now, this is interesting. Galileo, one of the ways he made a living was he made compasses. And by compasses, I mean the kind that you use to draw circles, but these were no ordinary compasses. Galileo, he didn't do anything halfway. Those compasses did a heck of a lot more than draw circles. He would put calibration marks on these, to where they were an early form of slide rule. Now, you see this book? This is the manual that went in with it. That other book that you saw, that first big book he's proclaimed for, the Sidereus Nuncius, it's written in Latin. Whenever you wrote something for the academia, upper level, educated men, you wrote it in Latin. You didn't write it in your native tongue. But this was written for engineers as well as scientists and academics. So it is written in Italian. But this It was just unbelievable the things you could do with a set of Galileo's compasses. For instance, they were used by bankers, merchants, craftsmen, engineers, surveyors, and astronomers. They were used for figuring out the elevation of cannons, to figure out how to fire a gun, a big cannon. Currency conversions, calculating interest. You could extract square and cube roots with them. Duplicating areas of geometric objects. It was just a heck of a instrument that he made. And there's a plumb bob that went in, he added in there for surveyors, a weight on the end of a line so that a surveyor can determine straight down line. Now, here is a picture I took of this painting. It didn't turn out very well because of the glare, but here is a better copy of it I got off the web. This is a painting of the meeting between the great English writer and philosopher John Milton and Galileo. How many of you are familiar with John Milton? Guy who wrote Paradise Lost. He idolized Galileo. Thought he was one of the greatest thinkers of the time. So much so that Galileo is the only one of his contemporaries that is actually mentioned by name in Paradise Lost. So, I was thrilled to see that because I had read about that when I was a kid, their meeting.
So it's Galileo on the right?
That's Galileo on the right. He was old by then, and he had lost his sight, partially from looking at the sun through the telescope. That was not a good thing. He had a cataract. He had more than one cataract. And probably damaged his retina too, who knows. But he discovered sunspots. But he also, a little too late, figured out how to project the sun onto a screen and see sunspots that way. Oh, I hit the wrong button. Galileo came up with the idea of the pendulum clock. Until Galileo came up with the idea of the pendulum clock, clocks were notoriously inaccurate. They'd lose time. In fact, just a block away from the museum, there's a tower where the very first clock that ever existed was installed. Still there, the tower is. The clock somehow got destroyed and a replica of it was put up, it was replaced in the early 1500s. But that clock was put, I forgot, way back. I think it might have been the 1100s or something like that. That very first clock was put in that tower. But the way Galileo discovered that pendulums were such accurate timekeepers was, back in those days, people seldom took baths. And within the churches, they would have incense burners swinging back and forth in order to mask the smell of the gathered humanity. And Galileo was noticing, it doesn't matter how low that pendulum gets and it swings, because it gradually gets lower and lower. But he noticed, it looks to me like it takes the same amount of time to go from one end to the other, regardless of how high that pendulum is going. So just to check, he used his pulse. And sure enough, it took the same number of pulse beats for that pendulum to create each swing up and back. so he said, this could be a way of keeping accurate time. So he designed the first clock, but the pendulum clock. Clocks have been around for centuries before that. But he designed the first accurate clock, but never got around to building it. His son started to build it, but died before he finished it. This is an actual, somebody in the 20th century actually made the clock and it worked. But the first person to actually make a working pendulum clock was Christian Huygens. How many of you have heard of him? The first guy to see the rings of Saturn. Galileo turned his telescope on Saturn, but he had really crummy optics. That telescope's optics were so bad it couldn't resolve the rings into separate rings that are separate from the planets. He wrote in Sidereus Nuncius that Saturn had ears. And so Christian Huygens was the first one to make a telescope good enough to where you could see that the rings were separate and going around the planet. By the way, Christian Huygens was a big rival of Isaac Newton. Huygens said, people in English call him Huygens, the Dutch call him Huygens. Huygens said that light exists in the form of waves. Newton said that light exists in the form of particles. Who was right? Both. We now know that light possesses a wave-particle duality. But for centuries, there was a big contention going on. Started off by Newton and Huygens as to what was the true nature of light. Was it a wave? Was it a particle? Yeah?
That clock had shown that pendulum in there. Is there a spring or something?
So, yeah, there's a gravitation, that weight. You wind that weight up.
So it's a weight.
Yeah, That weight unwinds the string up there that turns that. Yeah. Now, this is a 1800s built demonstrator of some of the principles that Galileo found out about gravity. He was the first one to figure out that when something falls, it doesn't fall at a constant speed. It gets faster and faster and faster if you neglect the air resistance. And you can if the object is really smooth and round to where the air doesn't give it much resistance. The reason why a feather falls less fast than a hammer is because of air resistance. It has very little mass compared to its surface area, so it just floats down. Galileo proved that all objects, if you neglect air resistance, fall at the same rate. He went on top of the Leaning Tower of Pisa, took two cannonballs. One of them, say, weighed maybe 20 pounds, the other weighed 10. And they were smooth and round and very dense, so that means that air resistance would not have much effect on them. He dropped both of those cannonballs, vastly different weights, from the top of the Leaning Tower of Pisa. They both hit the ground at the same time. Right? Now, later on, in 1970 or 71, an astronaut on the moon, where there is no air, there's gravity on the moon. The moon has 1/6 of the gravity of Earth, but he proved that gravity pulls things regardless, at the same rate, regardless of their weight, because I remember seeing this live when I was a kid. He took a feather and a hammer, dropped them on the moon, and they hit the ground at the same time. No air. Now, Galileo showed that every time, for every second, the thing fell, it got faster and faster. And if it's going out laterally, if you throw something out horizontally, it's going to fall in a parabola. For instance, these rings are equally or horizontally spaced the same distance apart. So when you let a ball roll down here and it goes off, it takes the same amount of time for it to go the horizontal distance. In other words, it's going to take the same amount of time for it to go from here to here, as to here to here, as to here to here, as to here to here. So horizontally, its speed stays the same. Vertically, its speed increases. Okay? The ball goes through here. You measure that distance. Twice that distance horizontally away, that ball falls 4 times the distance it did when it went from here to here. See, this is the second ring. 2 squared, 2 raised to the second power, 2 times 2 is 4. Here's the third ring. By the time it gets here, it has fallen 9 times farther than it did here. 3 squared, 3 times 3, 9. Fourth one, 16, it has fallen 16 times farther than it did here. 4 squared, 4 times 4, 16. A parabola. If you drop something straight down, that's the way it's going to go. Every second, it's okay if it falls the first second at a certain distance. The second, it's going to fall 4 times that. The third second, 9 times that. Okay? So, he was the one that discovered that. Newton was the one that explained why that happened. Galileo, for some reason, never realized that there was a force pulling stuff down. Oh, wrong way. Guess there was anything I forgot. So, toward the end, when we got to the end of the museum, this was the freaky part. We go look at these ornate transparent globes, and in this one, it's Galileo's thumb. And this one, this is Galileo's index finger and his tooth. One of his teeth. Now, the thing about it was, before Galileo, see, this was a way of honoring him. Before that, when people honored saints or whatever, they would put their bones or other parts of their body on display. He was the first secular person, the first man of science. By the time, this was the late 1600s. By then, everybody revered him. And he was considered to be one of the greatest men that ever lived. And so they decided to, back then, honor him the way they did saints and so on. They enshrined some of his body parts.
What did they preserve it in?
There's nothing but air in there, as far as I know. I think now they got helium in there, but I think at first they did not.
Where's that tooth in that picture?
It's right here. You see it? Here it is.
Oh yeah, I see.
Yeah, I think it is. But the main part of his body, though, that, by the way, because he died on the outs with the church, his body was buried on unconsecrated ground. But 50 years later, when people said, this is such a great man, and the church says, hey, yeah, he can be buried on consecrated ground, then they did this and put his main body in a very nice tomb with his daughter, who was a nun. He is entombed, his body is entombed with the body of his daughter, who was kind of his secretary, as it were, and kept records of all his stuff, everything he did. So that is pretty much the end of it there. Does anybody have any questions?
Yeah.
Yeah?
The Galileo compass, how does that work?
The Galileo compass?
Yeah.
Well, I mean, he had different scales all over it. It's kind of like if you're familiar with a slide rule.
The slide was based on logarithms. I don't know what to look at.
Oh yeah, logarithms were known back then. I don't know exactly when, but I think it was 1600s or something like that. What was his name? Napier. Maybe they weren't known. They might have been linear. I don't know. All I know is that you could do all that with it. He had it calibrated like that.
I'll Google it.
Yeah, Google it. It could be. Maybe they didn't have logarithms. Maybe it was all linear. I don't know. Yeah.
Yeah, when I was over Florence, I thought I read that somebody got up his bones and burned them.
No.
Well, that's a falsehood.
That's a falsehood.
Yeah, but somebody's bones were burned up in the church.
Yeah, a lot of people. Well, when Bruno, his whole body
I'm
was.
talking about different.
Yeah. No. Do we have any time for anything else? Okay. I was going to tell you about how Newton came to invent the reflector telescope quite by accident. Now Newton had heard that different transparent media bend light to different degrees, but he didn't believe it. He never, before he did anything, he always did experiments himself to verify to himself that, something is the way it is. Well, in order to make a refractor telescope that gets rid of false color, and as those of you who know about the simple telescopes like Galileo and everything, they were simple lenses, and they not only magnified things, but the glass acted as a prism and put false rainbow colors around objects. And so that was a major problem, trying to figure out how to make a refractor telescope that didn't put this false color around an object that kept you from seeing a lot of detail. And so they knew that if you could come up with two glasses, each of which bent light at a different angle, that you could make a telescope that would, the first element would introduce the false color, and the second element would cancel it out. So what Newton did, he wanted to find out if all transparent objects bent light to the same amount. So what he did, he was able to get a hold of a piece of glass, and he measured the angle that the light got bent. Now we know today that a transparent piece of material bends light based on its density. The more dense the transparent medium is, the more it bends light. That's why they put lead in crystal chandeliers, because it makes the glass more dense and makes it bend light more and makes it give all these pretty colors. But anyway, Newton, he had a piece of glass, he measured the angle, and he said, well, I don't have anything else transparent. What am I going to use? Well, he was there by the ocean. He went and got some salt water. Put a mirror down in it so he could measure, the angle the light was not just from being reflected, but bent by. And when he measured that angle, it was the same as it was for the glass, because it just turned out that the density of the seawater he had got was the same density as the glass. Because of that, he determined that all transparent mediums bend light at the same amount, and it is impossible to make a false colorless lens. So he went on to invent the reflector telescope. So anyway, a little bit of lore there for you. I was first told about that by my physics teacher, Percy Wimberly, a man who was so tough that we called him No Mercy Percy. Yeah.
The astronomical clock as well as the mechanical calculator, wonder how those worked back then.
Well, those were analog, and they just moved them relative to each other, and they were just manually turned, and they weren't powered. They weren't self-powered. It was the relative position of dials relative to each other,
I bet I could type in any of those on my smartphone and get the Wikipedia encyclopedia.
You might, yeah.
In my ignorance, I seem to recall that if you had a glass with two different liquids in it,
Mm-hmm.
of different density, one would be at the top and one would be at the bottom, put a straw in that glass, and you'd see the different diffraction as it went.
Yeah, you will. You will have, first of all, you will have one bend due to the bending of the first liquid, and then you will have a second bending due to the second. Yes, you sure will.
Don't make you drink.
Okay,
Okay.
let's have a hand for you.
If you're interested, I have another presentation on doing photometry. If you're interested in maybe trying to take your 8-inch telescope or larger and maybe finding an exoplanet, you want to know how to go about doing that, I've got a presentation on that. And any of you who are interested in space flight, you mentioned my book. I have some copies up here. If you want to know about how the U.S. can become the leader in spaceflight in the 21st century and what's holding us back, you might want to read that book.
Okay, thank you. It seems like Rick and his wife Julie here had a lovely 30th wedding anniversary trip. I asked Rick during dinner tonight how he was able to stay married 30 years, and he said that his wife always lets him have her way.